yeah, good morning everyone. We have a kind of a schedule today. So first I'm going to talk a little bit about some general methods for predicting facial information from face images, like soft biometric information like age and gender of people. And since this is actually a very sensitive topic, my research is more focused on actually protecting that information rather than exploiting it. Later after this section, we will have a tutorial where we will work hands-on doing some of these results that I'm showing ourselves, so doing some predictions on a small image data set. But yeah, let me start with the talk, and later we will get more into the hands-on section then in the tutorial. So yeah, the topic will be basically about biometric face recognition. And there are basically two subcategories of biometric face recognition. So there is basically the identification of a person. So imagine you have a picture of a person and you have a database and you want to just see whether the person is in your database. A typical application would be, for example, they have that at certain companies that you don't need even a key anymore. You just walk by a camera and the door opens automatically. So there would be a typical identification problem where this is kind of a useful technology to enable that. And the verification, that is it's kind of related. That is basically matching two images of a person and see if that's the same person. So one typical example would be, for example, an airport scanner, or also this door that I just mentioned, where you first show your ID, where there's a picture of you on the ID, and then you are there in person in front of the camera, and it checks whether you are the same person. So basically, verification and identification is kind of related. So in order to do identification, you also need to do the verification task. So identification is a little bit more tricky, because you do the same thing as in verification, but with many more people, basically. So yeah, typical applications are these security cameras, for example. And actually, when I just came here, I came here from the US, went to Frankfurt, and with my German passport, I also had to go through something like this here in the corner. They have like these automated booths now, so there's basically a scanner. You have to scan your passport. There's a camera that checks whether it's really you, and then you can pass through. But I mean, face recognition can be useful. Like I just said, there are these applications that make life more convenient. So instead of having a person sitting there the whole day and just checking, oh, this person is the right person, okay, we just use the automated camera to make this a little bit smoother. But it can also be kind of easily exploited. So this one is actually an article that was published in the New York Times like last month, 3 months ago now. And what the reporters did here, these were just general reporters. They didn't know anything about machine learning before. They just sat down and thought, okay, let's see what we can do with this technology. So I forgot how long they took, but maybe 2 or 3 weeks. They sat down, learned a little bit about machine learning and deep learning. And then they accessed all the webcams in New York, and I think this should play here. Yeah. So they accessed the cameras and collected a lot of images of people walking by in New York, and basically they could then identify this is a professor walking by. So they could basically track where people are going, and with just using open source software and publicly available cameras. And you can imagine, I mean, there are a lot of use cases where this is actually not a good thing, because you can track people, which is probably against what the people want. I mean, who wants to be tracked all the time, right? So my research is also focusing on protecting information from face images. And particularly though, I focus on soft biometrics. So I mentioned biometric face recognition, which is recognizing the face. This is the face is then a biometric attribute. But there are also these called soft biometric attributes, which are properties of the face that is not the face itself, but certain attributes that can be deduced from it. So for example, let's say this is John Doe. This is not really John Doe. Maybe some people notice who that is. So maybe I can also have a small competition. Or if you have a leftover prize, we can have someone predicting who that is. So you have, for example, the gender of the person, the age of the person, the race of the person, or medical information that can be abused. So there are a lot of companies going on Facebook, collecting images and making certain surveys or deducing information that they shouldn't, because people usually don't agree to that. So I also just had to sign a form that, for example, for the recording, it's okay, that's the proper way that you ask people. So not everyone gets asked when these information get deduced. So our goal is also protecting this information. But before we go to the protection part, I just also wanted to show you how easy it is really to extract these types of information nowadays with deep learning. I mean, deep learning is cool technology, but I mean, it makes certain things easy. Some things we are supposed to do, some things we are not supposed to do. Right now I'm showing you maybe what we're not supposed to do, just extracting information without consent. So first I will focus on the gender, just predicting the gender of the person. And actually this is so easy that I only want to spend one slide on it. This is something you can just readily do. You just use some off-the-shelf machine learning or deep learning model, give it a data set of labeled images, let's say 50,000 male and 50,000 female images, and then can just easily train a classifier that has a 97 to 99% accuracy. So in this case, I just used off-the-shelf ResNet model that is ResNet in the heading, ResNet 101, a residual net with 101 layers. We briefly, there was a talk yesterday covered a little bit about residual and dense networks. It's just a very popular architecture, and giving it approximately 100,000 images, you can in 120 minutes get it's a little bit overfitting, 99% training accuracy and 98% validation accuracy. I think the test accuracy is a little bit lower, 97.5. And I didn't really fine-tune that model. I honestly just used the standard parameters and just let it train, and you can see how easy it is to really already get a good result. Yeah, and I have a code here. If you will also maybe upload or share the slides if you want to find that useful. You can play around with that. I mean, this is really not a research project. I just did this to show you already how easy it is to reduce the gender. So, because gender is so easy, I want to focus now on a little bit of I would say more tricky problem, which is the age of the person. So this is not a classification problem now anymore. This is an ordinal regression problem. So in supervised learning, supervised learning is a subtask of machine learning where we have data and also the labels. But there can be different kinds of labels, so different types of information. There's, for example, category information, like here on the left, the color. These are categories like green, red, blue, or also the gender, male and female. So this is information where there is no particular order. These are just the classes, and usually we can't say green is greater than red or red is greater than blue. That doesn't usually make sense. So these are really distinct categories. Then there's information here on the right that is like continuous. For example, if you think about a t-shirt, and this is maybe a table summarizing properties of a t-shirt, the left would be the color of the t-shirt, the right here to the right would be the price of the t-shirt in a continuous scale. And then you also have the size of the t-shirt, which is maybe M, L, and XXL. So that looks like a classification problem. So we have M, L, and XXL. These are different categories. But now the difference between this and a normal classification problem is that there is a certain order. So we can, for example, say M is smaller than L, and L is smaller than XXL. So there is a classification problem with some additional information. And we can actually use a classifier for that, but it would be useful to not waste the information, the additional information about the order. And this is a so-called ordinal regression problem, or also ordinal classification, which is somewhere, I would say, between the normal regression task with a continuous label and the normal classification task. And yeah, for ordinal regression, we call this either ordinal classification or regression. It's some people call it either way. So let me just use the term ordinal regression for now. And there are also two subcategories. One is the real ordinal regression, and one is the ranking. So what we have is now a rank order, so Rk to R1, or the other way around. And there's a certain order, like with the t-shirt size. And we can then order the types of information, but we can also have a particular score. If you think about Amazon reviews, for example, we have these stars, like a 5-star rating, 4-star rating, 3-star rating, 2 and 1, or movie reviews. So there's this type of information that we have for order, but we also have a little bit more information. We have like this particular value. So what I mean by that, by a ranking problem, we usually just order things. So I don't watch movies very often because I don't like movies, but let's say I pick just 3 movies I'm familiar with, and I hope you don't get offended, but I'm ranking Blade Runner a little bit higher than Star Wars. Sorry, Jacek. And Star Wars a little higher than Star Trek, and sorry about that, Star Trek fans. So a movie ranking, like ranking a movie from good to, so very good to good, that would be a ranking problem. And age prediction is a little bit more than that, so we can have a ranking. We can say 18, oh, this doesn't make sense, it should be actually the other way around. So 18 is smaller than 29, right? It's early in the morning, sorry. Younger, yeah. So just imagine these are flipped, these little arrows here. Anyways, so we have a certain order, 18, 29, and 41 years old. And instead of having just the order, we also have this absolute information, we have the number. So in ranking, we just care about the order. In order regression, we also want to predict this particular value. And okay, we can maybe model age as a regression problem because we have the years and there's a very small gap. However, we can also make the argument age prediction is an ordinal regression instead of a regression problem, because we can say age is a non-stationary process. So if you think about it, a person between, let's say, 70 and 72, there's maybe a very small difference between how the person looks. However, if you have a child that is like 5 years old and 7 years old, you can see a bigger difference. So there's not the same distance between each age label. So we can say this is maybe a non-stationary process. And the secret why I actually did age prediction is at first it was one application in my hiding soft-biometric information task, but also, I mean, we have a lot of face images online available, which is why this makes a good case for deep learning actually, where it's not so trivial to use classic methods for deducing age from face images. So, and for that we developed one method that we call Coral. That is a consistent rank Logits model for ordinal regression for deep learning architectures. So how that works, how we do the ordinal regression with our deep learning framework. And I should mention in the tutorial we will see about different methods. So this is just one out of 1 million, not 1 million, but maybe at least 20 different approaches to doing ordinal regression. But this is one that is particularly simple to implement, and we will actually implement that later in the tutorial. So here in this model, how this works is basically we take an age label here, like in the upper left corner, and then what we do is we break it down into binary classification tasks. So binary classification task is like the gender prediction, like male or female, assuming that gender is binary, which is not the case in every country, but let's just assume gender is binary because that's how the data set is labeled. That would be then binary prediction task. And then we take an age label and break it down into 29 of these prediction tasks. So what we do is actually the person older than 1 year. Is the person older than 2 years? Is the person older than 3 years? So each question would be basically a binary classification task. So we do that, so we have this extended label set, and each on the right, each gives us a probability that the person is older than a certain age. So we end up with 29 of these binary classifiers. And in order to get the label, we just sum them up. So there's basically a sum over the predicted probability. So we can say at a threshold maybe above 50% probability, we can say, okay, this person is older than 1 year, older than 2 years. So we can convert the probability into binary zeros and ones, and then we just sum over them to get the age label. This architecture is basically a standard ResNet architecture. So we will also work with the VGG16 in the tutorial, but it could be any type of deep learning algorithm. And the trick, or not the trick, but the approach is basically just replacing the last layer by this Coral idea. What we basically do is very simple, and I will get into the moment why we do this like this. So we have the last layer, let's say this is a fully connected layer, and then, but instead of a normal fully connected layer, or multi-perceptron layer basically, we have a weight sharing here. So we share the same weight between this activation unit and all the subtasks. However, each task gets a unique bias unit. This is basically shifting the threshold. And the reason why we do that, I will get to that in a moment. We could also not share the weights, but there's one particular downside of that. And we will also explore that in the tutorial. Okay, so like I mentioned, this could be here on the left some arbitrary deep neural network. Then we have the Coral layer, and like I said, we are summing then these probabilities. So the probability whether the person is older, let's say we can say at 50% it's a yes, otherwise it's a no. But this is also arbitrary, we can maybe modify this, but 50% makes sense because it's just in the middle between 0 and 100%. Okay, so and the reason why we do the weight sharing in the Coral idea is basically that we want a rank consistency. So that means that this is satisfied, that if I have a person that is 30 years old, and I predict that the person is older than 1 year, then the person is older than 2 years and 3 years, that should be a continuous or cumulative function. So it wouldn't make sense if I have a person that is 30 years, it wouldn't make sense if I predict the person is not older than 1 year, but older than 2 years. That is a conflict. That doesn't make sense, basically. So we want to have this kind of consistency between the binary tasks. And in order to ensure that, we basically use this choral idea. And this paper that we had on that is basically all about proving that this is true. So it looks like a very simple idea, and it's very simple to implement, but the core idea is basically having a proof that this is satisfied if we share the weights. So in order to get this rank consistency, because the weights are shared, we will need the biases, the bias units, the thresholds that we add to them, also in an order. And in order to, in these, so the paper is basically about showing that these are ordered even if we initialize them with random values. So we have basically a very strong, or the guarantee that these will be ordered, these bias units. The network will automatically order them. And then if they are automatically ordered, then also this is satisfied. And then we get a nice cumulative function for predicting the age. So I won't go into the mathematical details, but if you're interested, we had, this is currently on archive. We just submitted this recently, so it's still in review. But if you're interested, the mathematical proofs are all in here, which I think are a little bit too tedious to go over here. But anyway, so just to show you how that looks like, again with the rank consistency. So there is a related method that is the first deep neural network with using these extended labels by Niu and Zhu and Wang and Gao. So this is on the left. It's a very similar idea, but they don't, for example, do the weight sharing. And if you don't do the weight sharing, you can see there are these inconsistencies. So I randomly picked one example where I wanted to predict the age of the person. I think here it was 26. At 26 there's this inconsistency here. So you're basically predicting that the person is not older than, let's say, 25, but then it's older than 26, or the person's older than 26, which is kind of a conflict. And our idea was that we can fix this problem, we can get better predictive results. So on the right is basically the cumulative function of the binary classifiers for this choral framework. And in order to test that, we considered different data sets. So here are the different phase data sets that we considered to check whether our hypothesis is, which is making this consistent, improves the results. So in order to check them, we considered different data sets. And we will be working with one of the data sets in the tutorial. First, I was focusing for the tutorial on this effort data set, which is available on the Jupyter Hub server, but turned out to be a little bit too expensive to train. So for the tutorial, we will focus on the smaller subset, the UTK phase data set, which is, I think, only 100 megabytes. So I also uploaded it in the Jupyter Hub, so we can use that in the tutorial. And you can also see there's a huge difference in the range of the ages, basically. So for some ages between 15 and 40, 16 to 17. So it's also, there are different, some data sets are more challenging than the others. And this one, for example, why it's 15 to 40, this is actually interesting. I think this was collected also without consent. There was a Chinese website that is similar to Facebook, and only for high school students though. So they basically collected images of high school students from this website. So the oldest high school student is now 40 years, which is where this comes from. Yeah, anyways, it's also interesting because these data sets are very imbalanced. So one idea of our paper was also to add a certain importance weight to the choral framework. And even if we add an importance weight to each binary task, we can guarantee the rank order. So we won't cover the importance weight in this talk and tutorial, but it's also a nice add-on to deal with imbalanced data sets. So how the results look like, it's really a lot of numbers here. But usually when you read deep learning papers, it's always you focus on the one that is in bold. And usually, coincidentally, the bold one is always your method, because your method is better than any other method. Yeah, but anyway, so we compared different approaches, and we found that fixing the rank consistency issue indeed improves the performance across all the data sets. And we used here the ResNet 34, but I also tested this on other architectures. And also one thing about deep learning is, what is a little bit tricky, is how we initialize the weights. So usually there is no reason to pick one random seed over the other to generate the initial weights, but you can get hugely different results because deep learning, it's a non-convex optimization problem. And depending on where you start, you can end up in a different local optimum. So it makes sense usually to run the method multiple times to make sure that this is not a coincidence. So what I did here is I ran each method 3 times with a different random seed, and then you can see the results vary a little bit, but they are in this case very stable actually. So, and on average our method is slightly better than the others. And I should maybe say what these abbreviations mean. So this is basically CE, CNN, sounds weird, but there's a cross-entropy CNN, which is basically just using a normal classification layer at the end. This is the other method that doesn't have the rank consistency, and at the bottom that is our method with the rank consistency. And you can see the gap between the cross-entropy and the auto regression one is also very small, it's only 0.4, and our method also again improves about 0.35. And these values, I should say, this is the mean absolute error. So that's on average the difference between the true age and the predicted age. And it's actually pretty good if you think about there's an age range of, let's say, 40 years. On average, you only predict the person to be 2.5 or 2.6 years older on average, or younger. So that is actually pretty good. So it's actually probably more accurate than what I could do. If I see a person, I'm actually not that good that I can say by 2.6 years how old the person is. Okay, so yeah, and if we add the weight, importance weight that I just mentioned, I won't go into detail, then we can even make both methods better, so the order regression and the choral CNN. And you can, so with this importance weight, we also still have the guarantee for classifier consistency. And just briefly, the main idea behind this importance weight is that if you convert the age label into these binary tasks, you also create a sort of imbalance. So you will see a lot of ones on the left hand. So the 1 is basically predicting that the person is older than 1, older than 2, older than 3, because many people in the dataset are older than 1, for example. And on the other hand, you will rarely see the older people in the dataset. Usually, most of the people are somewhere in the center. So this importance weight takes into account the distribution of the people in the dataset, but also the imbalance that you create by making these binary tasks. And by that, we can also improve it a little bit. And yeah, so I actually, like I mentioned, tested this method on different architectures. This is a paper by Alfredo and Adam, who also presented yesterday, which is one of my favorite papers because of this figure, basically, because it's a really nice figure that shows all the common architectures. I mean, the paper is a little bit older, like 2016, but most of them are still being used. These are the most popular kind of neural network architectures. And the size of each circle here represents basically the number of parameters. So here, million basically. So, and you can see that larger network, more parameters is not always better. Here on the y-axis, this is the top 1 accuracy. Is it ImageNet, Alfredo? ImageNet accuracy, top 1 accuracy. So you can see bigger networks don't always do better. VGG16, like we discussed yesterday, is particularly still attractive because it's very easy to implement. But it's huge, takes a lot of time to train, and it's not usually the best. So what we can see, these inception networks are usually performing well, the ResNet. What is missing, because it's a little bit older, is the DenseNet. But anyway, so it's a nice figure illustrating the different architectures. And AlexNet on the left corner, that is mainly the first deep neural network that was really recognized. It's the 2012 ImageNet classification task network that was making deep learning basically popular. So yeah, and when I tried my method also using VGG16, which we will be using in a tutorial, and the inception network, we can also see that our method, of course, otherwise it wouldn't be a paper, also performs better than the other ones. Yeah. Inception is also interesting because this is a network that has also auxiliary losses. So it not only has a loss at the very end of the network, but also in between. So here I also use the choral in all 3 losses of the inception. Okay, so this was about predicting the age of the person, which apparently is also very easy. Now we will switch to the second part of the talk, where we are trying to hide information from face images. So again, we have this biometric face recognition problem, where we want to do identification and verification, but we don't want to obtain the soft biometric information. We want to prevent that. So we want to preserve the utility. So if someone has a database of images, let's say at the airport, the security scanner, or even Google, we want them to have a data set where they can still do the identification because it's useful, but we don't want them to extract any additional information. And why this is problematic, I mean, we also have the GDPR, which actually prohibits that. But of course, saying this is not allowed is not as strong as saying it's impossible to do that. So making it impossible to extract information is a little bit better than just saying you shouldn't do that. Because there are certain problems with soft-biometric attributes. For example, identity theft. You can just go over Facebook and take a picture of someone. You can predict how old the person is, the age, the gender, maybe the race, the health situation. You put this in some form and then just pretend you are a person who you are not, basically. You can abuse the data for profiling. You can look at, let's say, distributions of customers, which you maybe are not supposed to do. But also just the ethics. I mean, like doing that without even asking people, which is not a nice thing. So our goal was basically to perturb this information, to hide this information, while still ensuring that the image is useful. Because I mean, I could just, if I can say, okay, if my goal is just hiding this information, I'll make just a scrambled image, but then of course this is not useful anymore. So our goal is also to ensure that these face images still look like real face images, and that we can still use them for face matching and identity checking. And we have basically, I think, 4 different methods for that now. I will go first through the older ones, and which is from last year, and then going sequentially to the newer approaches. Because I think if I would introduce the newest approach, you wouldn't have the background information, because this network looks a little bit confusing, so I wanted to go through the older ones first, which is not the best one, but it illustrates the problem best. So what we have, our setting, what we have is basically we have a face matcher. We want to still be able to predict that 2 people are the same for the matching purposes. However, we don't want to be able to predict the gender of the person in this case. So we want to hide the gender information, but still being able to match the same person. For example, if we have a driver's license and a picture of the person, let's say from a camera, I want to say, okay, this is the person who is in the driver's license. And how we did that, we'll go over the details in a few slides, but the backbone of that is basically using an autoencoder. Because we can use, again, a generative adversarial network which generates new images, and we use that some in our later methods. However, the problem with GANs is basically it's for generating new images, so the image of the person will be a little bit different than the original image, and we want to preserve most of the information in the image. So an autoencoder, you can think of it as a fancy principal component analysis. So autoencoders and PCA are actually very similar. So you can, if you use a linear activation function, kind of build a principal component analysis by using an autoencoder. But the power of the autoencoder comes basically from the fact that we use nonlinear activation functions. And both parts, the encoder and decoder, are basically, in this case, convolutional neural networks. So we have a convolutional neural network that takes in an input image and then compresses it into a small vector. So the size is kind of arbitrary, but let's say a vector of 50 pixels, or not pixels, but values in some new dimensional space, smaller dimensional space. And then we could, for example, in classification, what we would basically do is usually having softmax output here and predicting certain properties of the image. However, instead of doing that, instead of doing prediction here, we take this vector again, and then we decode it back into the original image. And the goal of the autoencoder is basically to train the autoencoder in such a way that we can represent this in a smaller vector, but then when we reconstruct it, we get the same image back, basically, minimizing the error between the output image and the input image. So you can think of it basically as a compression network. And we use that basically to perturb our images in such a way that the gender information is hidden. However, the image is still almost like the original one, that we can use it for face matching. So our architecture, we call this Semi-Adversarial network, or SAM. It consists of one autoencoder and 2 subunits. One subunit is a face matcher, and one subunit is a gender predictor. And all 3 components are convolutional neural networks. So what we do is basically we put the image through the autoencoder, get a perturbed image, and then we have a loss function that makes sure that the matching is still accurate. However, the gender prediction is basically flipped. So yeah, the 3 objectives basically, retaining matching utility, ensuring that the face images are realistic, and then the gender is basically hidden. Actually, we don't really want to flip the gender, because if you flip the gender completely, if your classifier has a probability of, let's say, 98% male, and you flip that to 98% female, a person who wants to abuse your data set could also just flip their classifier. which is actually not desirable. So what we want is actually we want to randomize it. We want to be at like 50%, where it's very uncertain. Okay. And the reason why we call this semi-adversarial, maybe it's some weird name, but the reason is because I wasn't very creative, and this task is basically the non-adversarial task, so we want to still preserve the original function, but this one is adversarial, so we want to kind of flip the gender. It's kind of an adversarial learning task. And like I said, these are all convolutional neural networks. It's a little bit weird, but we use gender prototypes. It sounds a little bit fancy, but what we do is basically we found that this empirically works better, and there's no theory for that. It's just empirically observed that we add gender prototype information here. It makes our network work better. What that means is gender prototypes is just a fancy name for saying we take the average image of a male person, or the average image of a female person, and also provide it to the autoencoder. So we provide a gender prototype that has the same gender as the original image at this point, and the opposite gender prototype here. The reason why so what we do is also actually we have three versions of that. We have three, let's say, networks or types of network. One, we give the same gender prototype. One, we give a neutral one, which is the average over all images. And one, we get the opposite. We feed it the opposite one. And then we want to compare. We basically hypothesize that we add the opposite gender, it will flip the gender more than giving it a neutral gender. And if we give it the same gender, it shouldn't flip it at all. It's basically also for observation purposes to make sure our method is doing what it's supposed to do. So because I think I was slower than I thought, I won't go into too much detail about these prototypes. They are basically just combined with the original image. It's just adding them. It looks fancier than it really is. We also chose fancy names like proto-combiner, but it's basically just concatenating the prototypes with the original image. And like I mentioned, there are three loss functions. One is basically the pixel-wise similarity between the input and the output image. One is the loss term related to the gender. So we want to flip basically the gender. And one is the loss related to the matching. We want to still ensure that the face images look or can be matched between two different poses of the same person. But now a little bit less math, because this is dry, to show you some examples. So here, this is a bit pixelated on this big screen, but here are four examples of how the outputs look like. So in the top row we have the original images, and in the bottom row we have the modified images. So in each case, we try to, so it's not always the case, but we try to aim for 50%. In some cases, we flip it a little too much, so we flip 98% female into 99% male. And this is actually based on these auxiliary classifiers. Of course, one might say, okay, if we use these auxiliary classifiers, these are our own, so no company is going to use that, so our method is basically useless. So these were only used during training, these convolutional networks that I showed you. So I just go back. These two parts, these are only used for training, and then they are discarded. So after training, we just throw them away, basically. And for evaluation, we replace them with commercial classifiers, something that you can buy from different companies that allow you to do face matching, or gender classification. We also tried open source ones. For example, IntraFace is an open source classifier. And in this paper, in this first paper, we only tested one commercial gender classifier, one commercial face matcher, and one open source gender classifier. Later we tested, I think, 5, 6, 7 of them. So we want to make sure that our method works with all of them. And these are ones that our method has never seen before. So when I look at the results here, so these are some ROC curves, receiver operated characteristic curves. And the optimum is basically a line that is just like this upper edge here. And the random prediction would be the diagonal. So this would be the diagonal. And this is what we want to achieve when we want to perturb the gender. We want to be able to not deduce any gender information. So we are aiming basically for this diagonal line here. So the more diagonal it is, the better, basically. And here we are evaluating the performance of the gender classifier. And if we apply our method, so like I mentioned before, we have these three different types of prototypes. We had the similar gender or same gender, the neutral one in T, and the opposite gender, OP. And here, reference 21 is an earlier method by Ottman and Ross, where they tried something similar using a more geometric inspired approach. So we are comparing it here to this, or we are evaluating the IntraFace gender classifier, and we can see if we use the OP, the opposite gender, we achieve in almost all cases a random gender classification, which is our goal basically. And you can also see if you use the neutral gender prototype, this is less confounded, and with the same gender prototype, this is even less confounded, which is a property that we want to see. So the more kind of opposite the gender prototype information is, the more heavily the image is perturbed, or the gender information is perturbed. So this is about gender classification, but like I said, this is maybe easy to achieve if the images are scrambled. Our goal is, although, to ensure that we can still do the face matching. So when we look at the face matching performance here, you can see we still do pretty well. So there are many lines here, there's a lot of stuff going on, but this dotted line at the top is basically taking the same image before and after. So maybe to go back to my, that's maybe too much, but to this cat image. So this is basically doing face matching on this input and this output image. So the other ones are though doing this, that we have a picture of a person in one pose and a picture of the person in a different pose. So these are different pictures of the same person, but this is more like the real case scenario where you go to the airport, you have your passport, and they take a picture. So the real goal is basically to make sure that you can identify people in different poses still. So all the other lines, I will stop in a second. So the other lines are basically showing the performance, face matching performance if we match people in different poses. And as you can see, we do still pretty well here. Of course, not so the threshold is basically the blue one. That is the original face matching performance, because face matches are not perfect. And we are very, very close to this blue line. I mean, relatively close, so we still do very well. And this is basically the line by the other methods, where they actually have to say, for fairness, they didn't have the objective to make sure that the images can still be matched. They had just an objective to fit the gender. Okay, so this was our SAN method. We had very quickly different improvements. Here what we did is we diversified, we made sure that the data set is more balanced, because one issue is that certain subpopulations are overrepresented and underrepresented. For example, face image data sets have usually a lot of people with a white, light skin color, and people with a darker skin color are underrepresented, also female people, so we wanted to make this more fair. Also had gender prototypes that are for different subpopulations. Another method that we just published last week actually is this flow SAN, where we have more control over the face perturbation, so where we can basically regulate more like how the threshold between matching accuracy and gender flipping, so that we have different outputs. We basically have multiple SANs in a row. And then the newest one that is not published yet but just submitted is the PrivacyNet, where we basically do the same thing with multiple attributes. Before we only had gender, now we are also having age and the race of the person. Yeah, this is basically kind of a little bit different, where we use a cycle again with the cycle consistency, that we basically also ensure that we can regenerate the original face. But yeah, because we don't have time, I won't go into too much detail about that, and just wanted to thank you for attending this talk. And we